So this is Group 1's biomechanical analysis of cycling. There's a lot of material to cover here, so we're going to move pretty fast, but pause if you need to. Brief history here, but let's get past that so we can get into some of the interesting biomechanics going on. Some of the key components we're going to cover most heavily include posture and the pedaling action itself. So starting with the joint kinematics, we see that the hip, knee, and ankle are the main joints involved with their ranges of motion linked there, and note that the ankle can move much less than 20 degrees, as some people don't implement the ankle at all. This can vary based on level of experience as well as pedaling cadence, which is where you're going to see most of the difference at the ankle usage. And of course, the road or mountain bike cyclist can vary as well due to the difference in crank length, which changes the radius of the circle drawn by the pedal motion, and the saddle height, which will lift the hips of the rider up further away from the pedals, changing the range of motion as well. Now, the upper body's contribution is mostly for stabilizing the upper body to create a stable platform from which we can generate force at the pedals, and a weak core for doing this will create excessive recruitment, which can cause low back pain as well. Now, of course, all of Newton's laws are important, but the one that stood out to us when we were looking at the design of the bicycle is Newton's third law, as we see so much of the design based on those action-reaction pairings, as in the action of the rider's weight on the bike and pushing the bike forward, and then we see the reaction forces from the ground coming up and this double triangle design of the bike's frame to handle those forces, and then we see the force input and force output aspects from the pedal, transferring force from the rider's legs to pushing back on the ground, which propels the bike forward. Now, the seat of power describes where most of the force generation is coming from, which is the muscles and joints between the knees and hips, as well as the range on the pedal from the 12 o'clock to 6 o'clock position, which is also can be considered the downstroke or the power stroke or the extension phase. And we see a little bit of why that's happening when we see the hip extensors, knee extensors, and plantar flexors working together on the downstroke. And then as we retract back up, the dorsiflexors, knee flexors, and hip flexors all activate. Now, the downstroke, including the gluteals, quadriceps, and calf muscles, is the stronger part of the pedal, and the hamstrings, hip flexors, and dorsiflexors are mostly to reset the pedal back up to the top for another downstroke. So we can look at the motion here, but if we go to a still, we can break this motion down a little bit more clearly. So the posture that this rider is in right now has the wrists extended, forearm pronated, elbows extended, shoulders flexed to about 90 degrees and slightly internally rotated, slight flexion at the back, and there is definite flexion at the hip, knees, and a neutral ankle. If we correct this for what we would consider more ideal, we would see the hands move forward a little bit more so that the webbing between the thumb and forefinger are up in that pad. This would allow the spine to slope forward a little bit more, and this puts a little bit more of a balanced weight across the seat and the handlebars, creating a more stable platform. And we'll see why that's important in just a little bit. We can also see a little bit more of a relaxed posture at the top, which we would likely see slight flexion at the elbows and no internal rotation at the shoulders. And based on preference, we could even see the seat raised up a little bit, which would allow the rider to activate the calf muscles a little bit more and plantar flex a little bit. From the frontal view, we see why that stable platform at the handlebars is important, as we can see the rider bobbing side to side, when ideally we'd like to see everything in the sagittal plane, so we'd see nice vertical movement, which is more efficient, and it can also be linked to avoiding injury. As we see here with the lean to the side, we get more flexion at the hip, more flexion at the knee. In this case, we also see a varus posture at the knee, which can create lateral forces on the knee complex, which can lead to injury. The most important part of force generation is what bikers call the power stroke, and we mentioned before that most of the force generation is from the pedal coming from the 12 o'clock down to the 6 o'clock position. and we'll try to investigate here a little more as to why that is. So if we look at the torque generated by the quadriceps at the knee, that rotates the leg as a lever around this arc, and the output force becomes a linear tangent line to the circle that would be drawn by the leg if it could go 360 degrees. Now if we look a little further and remember that the hip activates to extend as well, we see that that has a similar lever action and its own force vector, which is slightly downward, following the tangent line of that radius. If we combine those vectors, we see that the output force of those combined vectors is tangent to the circles drawn by the pedal. And this is where that efficiency is coming from, and this also shows us how the body transfers force as it rotates around the pedal, because if we watch the tangent line become more vertical as the pedal continues around, we would see the gluteals activate more and the quadriceps relax a little bit more to create that more vertical combined vector. And we see that transfer of power between all the muscles around the entire circle of the pedal. So that's how we create a smooth force generation throughout the entire pedal rotation. And this is important for that efficiency and that implementation of all joints and all the muscles. So in summary, we have a stable upper body, good platform to generate force from. The hips, knees, and ankles all work together to rotate only along the sagittal plane to generate efficient force around the entire rotation of the pedal. And the output from the back tire pushes back. Newton's third law tells us that that will propel the bike forward. And I know that there's a lot going on there, but thank you so much for watching our video on the biomechanics of cycling.